Test, test. Test, 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 test. Test. I don't think it's picking up my microphone. Oh, there it goes. Okay, now I'm trying. So there's like a settings inside of Jitsi, and I've selected Natty mic. Let's see if that sounds better. It, it maybe doesn't sound better. It seems quieter, but I guess the quality is probably better. Okay, I'm using Chrome. You didn't know.
Hey, can you hear me?
Hey, I can.
Hey!
Woo!
Woohoo!
Woo!
We need the party parrot emoji.
Yeah. No. I'm trying to figure out how I can actually share my stream, my stream. Link to the stream. Let's see. Looks like it's changing automatically. There's about a 5-second delay. The video looks really good, but
awesome.
Yeah, there's a little bit of there's a window overlay for some reason where it says there was an error connecting your camera, but I don't actually see it on my screen. I wonder if it's in the window somewhere. Maybe I can delete it. Wow, there's a lot of output. Wow. I need to tell the Code Buddies people about all this. Oh my goodness. This logger's out of control. Let's see. There was. Error. Nope. It's strange. It looks and sounds really good.
Oh, that's good.
But I just can't find the link to share, and I also can't find. I'm even turn that off. I also can't figure out how to close this window.
Oh.
I bet if I just open my channel, it'll probably be there. Maybe. Oh yeah, here we go. Yeah, look at this. It's weird. The live stream.
Okay.
My channel will probably be there.
Oh yeah. There you are.
And it has that there was an error connecting to your camera. Camera was not found.
Yeah, I can see it.
Okay, I'm gonna try refreshing, so it's probably gonna drop me for a second. Yeah, look at this.
Okay.
It's weird. Let me grab that stream ID
Okay.
there. The live stream.
Okay. Oh yeah. There you are.
And it has that there was an error connecting to your camera. Camera was not found.
Yeah, I can see it.
Yeah, I'm gonna try refreshing. It's still there. It's gonna drop me for a second.
Okay.
Let me grab that. Well, that's weird.
It is.
Just one thing after another. I don't know how to fix that,
Me neither.
or even what that's supposed to mean. I guess I'll screenshot it and
Yeah.
figure it out later. It looks like that's a bootstrap error of some kind. Oh, this whole thing is bootstrap. I'll just. Huh. It's really strange.
Yeah. I sound good though.
You sound great. Do I sound okay?
Yeah, you sound fine.
Okay. Well, say levy.
Yep.
Yep. We'll figure it out later. Uh, let's see. So interactive SICP. I wonder if I share my screen, if it'll do anything differently. Okay. That might actually fix it if I just share my screen. Let's see. Do you remember where we were at last time?
Not off the top of my head.
Yeah, me neither. I have it in my notes. I can open that up.
Okay. Yeah, I think were we somewhere near the end of chapter 1 or
Yeah, or the end of 1.2 at least.
yeah. I can't remember how far we got through 1 point. Actually, maybe it was just 1.2 that we got through because the stuff with the 1.3 is not looking very familiar.
Okay. Yeah, definitely. It's new stuff. So let's look at the bottom of 1.2.
Yeah.
Oh yeah, counting change. I remember doing that.
Okay, yeah, I do remember doing that. Was that in 1.3?
That's 1.2.2.
Okay. Okay.
It's actually around the middle of 1.2.
Okay.
Prove that Fibonacci is the closest integer to theta n over square root of 5. Oh yeah, and Pascal's triangle.
Yeah, I remember talking about that at some length.
Yeah. And that do you remember that issue where we were getting
Yes.
yeah, they actually patched that and
Yeah, and then got kind of snippy, if I remember correctly.
yeah, a little bit. They're like they're like all the side numbers are 0.
Yeah, it's like Pascal's triangle shouldn't return zeros. It's like, well, that's the whole idea. It's an error handling function. So
Yeah. Well, at least it got fixed. Let's see. I guess we can talk orders of growth. It's the next thing. I don't know how interesting that is.
that might be like the big O stuff. I don't know.
Yeah.
Let me just do Command F. Orders. There we go. Orders of growth.
Draw a tree. Yeah, this is exactly.
Yeah, I thought we
big O.
talked about this at least a little bit.
I think so. We for sure talked about log. We talked about polynomial time.
Yeah, totally.
We talked about the Ackerman.
Yes.
What's the other stuff?
See, greatest common divisor. I think we talked about that. Testing for primality. That sounds familiar. Okay, the Fermat test. That I'm not. Did we do that one?
I don't think so.
That one doesn't seem familiar.
Fermat test. The Fermat test.
Yeah. Well, if you're going to Texanize it all the way. The Fermat test.
Yeah. The Fermat test.
I assume it's Fermat. I never actually took French, so.
That's got to be Fermat. Yeah.
Yeah, and well, I think I've told you before about my adventures attempting to speak French when I went to France. So I don't even think my pronunciation was that bad, but they did it to my advisor too. So it wasn't like they had something against me personally.
No. They were just.
They're just not very, yeah, they're just not very tolerant of pronunciation.
Oh yeah,
discrepancies.
Bordeaux.
Yeah. So.
Yeah.
Like I would try to say something like to a shopkeeper or something in French, and they would just look at me like, "Your French hurts my ears," and reply to me in English.
Oh, that's no fun.
Yeah. So. It's funny because most places will at least give you points for trying.
Yeah. Most of like in Italy, they would just kind of laugh and yeah.
Yeah, exactly.
Tubleron.
So.
Use the smallest divisor. Let's just start with Fermat test. That sounds good.
Okay. Sounds good.
And I can just read and then ask you.
Sure.
Okay. So, do we just say the big O log n?
Well, that's not an O. That's a theta.
Oh, okay.
So, I can't remember if we went over this in the previous section, but for some, so if a function is big O of something, then that's an upper bound. And then if it's little o of something, then that's a lower bound. And so if it's big O and little o, or sorry, I'm getting my notation confused. Sorry.
It's okay.
There's no, little o is actually something else. Sorry, it's big omega that's a lower bound. So if a function is both big O and big omega of a function of the same polynomial that only differs by a constant, basically like different constants applied to like say n squared or something like that, then a function can be said to be big theta of a particular of a particular value. So like again going with the n squared example. So
okay. So it's big theta if it's big O
if
and big omega only differ by a constant.
Right.
Okay.
So basically, so like if you get into like the mathematical definition of what big O is, it's let's see. I'll start with Wikipedia if I can, and if that doesn't give me an answer I like, I'll just whip out the CLRS. But
cool.
So
Bachmann-Landau notation.
Yeah, so here we go. The formal definition. This is from Wikipedia. Let f and g be two functions defined on some subset of the real numbers. One writes f of x is big O of g of x as x goes to infinity, i.e. all x greater than a certain threshold, if and only if there is a positive constant m such that for all sufficiently large values of x, the absolute value of f of x is at most m multiplied by the absolute value of g of x. That is, f of x is big O of g of x if and only if there exists a positive real number m and a real number x0 such that the absolute value of f of x is less than or equal to m times the absolute value of g of x for all x greater than x0. So like trying to think of an example. So like f of x, let's let f of x be x plus 1. Well, that's going to be less than or equal to, say, 2 times x, right? For all x greater than or equal to 1, right? So for in that particular case, you would say you would say your x0 in that case is 1. And so so that's big O. And then big omega is the same principle, but it's a lower bound. And so but you do the same thing. You find some kind of constant that it's less than or equal to for all, for all values above a certain threshold or something like, or greater than or equal to, sorry, for all above a certain threshold.
Right. Okay.
And so like if you wanted to prove like big omega in the case of the function I just used, you could set, your constant equal to like 1/3 or something. It just has to be positive. So it can be between 0 and 1. It just can't be 0 or negative. So in that case, so like to use, since big O is usually framed in terms of n, because n is usually like the size of the input, if your function is like n plus, say your function is n plus 1, then that is less than or equal to 2n for all n greater than 1, and then it's greater than or equal to, say, well, let's go with 1/2 n for all n greater than or equal to 1. So n plus 1 is both big O and big omega of n, because it only differs by a constant factor.
Okay.
So, which therefore would mean it's also big theta of.
Right.
of n. So that's what, when a function is described to be a big theta of something, that means it's both big O and big omega of a certain of
Okay.
whatever the given function is.
So I'm gonna try to like ground this in something. Um, is the idea, or do we prefer uh, functions that are um, big theta or that are theta?
Um, I would think it just gives you more precision. It gives you a tighter boundary, basically.
Okay.
I'm sure there are some functions that you can't say they're big theta because they're, or actually that would be an interesting thing to try and prove. But there's probably some functions out there that you can't prove a big theta boundary. Like you can only prove an upper bound or only prove a lower bound. So.
Hmm. Right. Yeah. We
So
talked about that a little bit.
it's just that if something is big theta, it's more of a known entity because we have reasonably precise upper and lower bounds. So we have a better idea of what we're dealing with.
Right. And then you can actually estimate things like computation time and
Right.
or precision potentially.
Exactly.
Okay. Good explanation.
Thank you.
Um, I'll have to go back and re-listen to your explanation later.
Okay.
It was good. Um, let's see. So, okay, so that's a working definition for the theta. And do we
Right.
just say theta?
Yeah. You can just say theta because there's actually no such thing as little theta for reasons I won't get into right now. So.
Okay. Okay, cool. So the theta of log n, or do you say of the theta log n?
Usually, yeah, theta of log n is
Okay.
fine.
Okay. Yeah, that makes sense. The theta of log n primality test is based on a result from the number theory known as Fermat's little theorem. Fermat's little theorem: if n is a prime number and a is any positive integer less than n, then a raised to the nth power is congruent to the modulo n. Two numbers are said to be congruent modulo
Oh,
n.
there's a footnote. You
Uh,
skipped a footnote.
oh, good. Okay. Good. Yes. Uh, Pierre de Fermat, 1601 to 1665, is considered to be the founder of modern number theory. He obtained many important number theoretic results, but he usually announced just the results without providing his proofs. Fermat's little theorem, it was stated in a letter he wrote in 1640. The first published proof was given by Euler, I'm sorry, in 1736, and an earlier identical proof was discovered in the unpublished manuscripts of Leibniz. The most famous of Fermat's results, known as Fermat's last theorem, was jotted down in 1637 in his copy of the book Arithmetic by the 3rd century Greek mathematician Diophantus, with the remark, "I have discovered a truly remarkable proof, but this margin is too small to contain it." Finding a proof of Fermat's last theorem became one of the most famous challenges in number theory. A complete solution was finally given in 1995 by Andrew Wiles of Princeton University. Do you, do you have any remarks on that, Danielle?
Just do you want to know what Fermat's last theorem is? Because I think I know.
Yes. I have a little book on it, but I haven't read it yet.
I think it's for yeah. Okay, so yeah, I just pulled up the Wikipedia page just to be sure. No three positive integers a, b, and c satisfy the equation a to the n plus b to the n equals c to the n for any integer value of n greater than 2. So of course, like we have the Pythagorean theorem, right? A squared plus B squared equals C squared. There's tons of cases of that, but there's no integers that equal like A cubed plus B cubed equals C cubed. There's no integers that would satisfy that that equation. So
Wow, that seems really simple but very tricky at the same time.
right.
Yeah.
Yeah, and yeah, so yeah, formal proof wasn't published until 1995, as they said. So
Oh, this is
that's
1994.
yeah. Well,
Oh, public.
he
Okay.
came up with it in 1994, published it in 1995. I think
Yeah.
that's what it says.
Yep. Yep.
Yeah. So
58 years of effort.
not too shabby, huh?
Yeah. Have you read the proof?
I have not.
That'd be interesting.
Real analysis was about as advanced as my math education got. And that was I think I've talked about that before, like having to prove certain basic properties of arithmetic just using a subset of the Peano axioms,
Right.
and that was like the mental equivalent of backbreaking work. I was like physically tired after completing those proofs.
Yeah. Yeah, that sounds uh like an Olympian feat.
Yeah, like we're taught things like the commutative property of addition, right? You know, a plus b equals b plus a. But you know, we're taught that in like elementary school. But we, you know, certainly at that stage, and most people don't ever think about, you know, well, how do you prove that mathematically? And I don't remember how to do it now off the top of my head, but I do remember making it happen. But there's, you know, based on those axioms, it is possible to prove that sort of thing, or prove that any number plus zero is itself, that sort of thing.
I mean that these things are kind of hinting at lambda.
Yeah. Oh yeah, totally.
Cool. Well, let's keep going and look at
Yeah,
some
yeah, yeah.
lambda.
Yeah, let's.
So there's a little more after that quote. It says the two numbers are said to be congruent modulo n if they both have the same remainder when divided by n. The remainder of a number a when divided by n is also referred to as the remainder of a modulo n, or simply as modulo n. If n is not prime, then in general, most of the numbers a less than n will not satisfy the above relation. This leads to the following algorithm for testing primality. Given a number n, pick a random number where a is less than n and compute the remainder of a modulo n. If the result is not equal to a, then n is certainly not prime. If it is a, then chances are good that n is prime. Now pick another random number a and test it with the same method. If it also satisfies the equation, then we can be even more confident that n is prime. By trying more and more values of a, we can increase our confidence in the result. This algorithm is known as the Fermat test. To implement the Fermat test, we need a procedure that computes the exponential of a number modulo another number. So we have this bit of code here called expmod.
Yeah, those consonants don't work well together, do they?
No. Uh, and expmod takes a base, an exponent, and a modulo. And we have a condition. We'll check if the exponent is equal to 0. If so, we just return 1. If then I guess we have is even question mark. That's going to be another function.
That would be my guess.
Um, if it's even, then we find the remainder of taking the square with the of calling x mod with the base. Oh, this is the actual checking. Okay, I want that condition. So we divide the exponent by 2 and then return m. Otherwise, do the remainder. We multiply base exponent mod base the subtraction of exponent 1 and okay. So what's that second tree doing?
Just a second. Let me take a look at it. Okay, so then if the exponent is even, okay, so it takes the remainder of it's making a recursive call and like squaring something.
Yeah.
And then calling it with a new, it's squaring, but it's then cutting the exponent in half. And
do we have?
And then dividing it by m looks like. So let's just start. Let's just do this old-fashioned way. Let's start in with the innermost parentheses and work our way out, shall we? So we've got this. Okay, so we're dividing the exponent by 2, and then that's fed into a recursive call of this xmod function.
Xmod.
Yeah, and the only thing changes is the exponent is cut in half, and then the result of that is squared, looks like. And then you take the remainder of dividing that result by m. Yeah.
Okay.
Does that make sense?
Yeah, the algorithm. Well, I mean, on somewhat.
Yeah, it would be nice if we had like clearer pseudocode for something like that. But
yeah, I actually looked at a JavaScript version, but that was even that made even less sense.
Okay.
Oof. Okay. Haskell. Wow, there's something called the Miller-Rabin primality test.
Okay. I'm a Ciba Veritasthenes gal myself, but admittedly, that's one of the slower algorithms. So,
Indeed. I've never even heard of that one.
it's actually very simple. So basically, you write down all the it's by hand it would be inconvenient for large values of n, but you write down or have some representation of all the numbers from 1 or actually from 2 to n, because you don't count 1 in it. And so you count, well, actually up to the square root of n would be as far as you needed to go. But so you take 2 and then you cross out all the multiples of 2. And if you happen to cross out your target number, then obviously you're done. Then you cross out all the multiples of 3, and so and of course 4 you've already crossed out, and then 5, and so on and so on. And then basically, if your number is still left standing by the time you've gone through all of these numbers, then you're good.
That's pretty cool.
So yeah. So like take 7. Let's keep it real simple. You would cross out, at 2 you would cross out 2, 4, and 6. 3 you would cross out 3, and then 6 is already crossed out. 5 you would cross out, and then you're 2, 7. So that means you're good
Hmm.
because you haven't crossed it out already. So.
What is that method called?
The sieve of, I think it's Eratosthenes. I might be mispronouncing the poor guy's name, but let me.
Oh yeah,
I'll put a link.
Aristophanes.
Yeah.
Neat. Oh, there's a GIF on the Wikipedia.
Oh, okay. You found it.
Nice. Yeah. I also posted a Haskell implementation um, of the Fermat.
Oh, cool.
It's actually like the second or third one because someone posts and he asked for code review, and then the response to it is pretty
Yeah.
good. Um, I'm pretty sure the dot notation is you say like 2 for the dot.
Let's see. Let me pull up that page.
Into is square into or toward.
Where are you?
The first answer.
Okay.
Where it's odd seems like a useless function. You never use its result.
Mm-hmm.
And then a little further down.
Okay. Ceiling. I actually don't know how it's spoken.
Yeah. It just means it's like a pipe to the right.
I think so.
And the dollar sign is kind of like a pipe to the left.
Yeah.
So it's like you're calling square root on the ceiling and the from it, and calling from integral with n. From integral might be a built-in.
Yeah.
And it just returns a tuple or tuple, 2 integers, a maybe of a tuple.
Okay. The sieve of Eratosthenes isn't quite n squared. It's big O of n log n. So.
Oh,
Good to know.
that's interesting.
Yeah.
N log n.
Yeah.
Huh. Oh, I needed to ask you sometime about that notation. I started reading a little bit of the Introduction to Functional Programming through Lambda Calculus,
Oh
and
yeah.
all of the examples are in that bracket notation thing. That
Yeah. Let me pull. I think I have an electronic copy of that.
ENF, is that what it's called?
Oh, BNF or.
Yeah, buckets an hour.
Oh yeah, Bacchus-Nauer form. Yeah.
Yeah.
What did you want to know about it?
Just how you read it.
Okay.
I don't understand it.
Okay, so generally in let's see, I think this is on the left-hand side, at least in at least if assuming you're dealing with the context-free grammar, which you almost certainly are. That you have what's called a non-terminal, and there should only be one. Okay, here we go. In BN form, okay, so chapter 2 in BN form, this is variable is defined as either the letter V or a variable with the prime character, the apostrophe, basically.
Okay.
And then so anytime you have a variable, it will ultimately be one of those things. And then a lambda term is either a variable by itself, or it's the single vertical pipeline usually means
Okay.
or open parentheses. And because things like parentheses and square brackets tend to have other meanings, like a regular expressions type context. If they mean the actual left parenthesis character, they'll put quote marks around it, as they've done here.
Oh,
So,
okay.
that means that yes, we're actually talking the actual left parenthesis character, and we're not using it, to group other components or something.
Okay.
So they mean the actual left parenthesis, lambda term, actual right parenthesis.
Okay.
Or it can go left parenthesis, lambda, variable, lambda term, and then right parenthesis. And so, yeah, it gives some examples at the, underneath. So like V prime, then in parentheses, V prime V, those are all lambda terms. And so, lambda V, V prime V, that sort of thing. And then the and then the next section, it shows you some more examples. So
Okay. Yeah, I need to look at that some more. It was really cool. I read the introduction and they were talking a little bit about normal order that came up, and it was right after we talked about it.
oh yeah, did you feel like a
Also.
genius?
Oh boy, did I. And until I got to chapter 1 and I was like, I don't know how to read this notation.
Oh, okay. Yeah, but it's just the vast certainly for programming languages, grammars are almost always going to be denoted by some kind of version of that style. So,
Cool.
in fact, I think there's even a BNF for BNF. So,
Of course.
because of course there is, right?
Yeah. Yeah, there can be one.
Right. Yeah. Because pretty much anything that can be expressed in terms of a context-free grammar can be expressed in BNF. That's the whole point.
Right. That kind of reminds me of a sort of brief video that Andrew Ung gave as like an hour and a half intro to machine learning
Yeah.
to a group of people last year, and he was talking about the project or the product manager's job, and he basically gave a sort of Venn diagram where on the left it was all the things that users like and want to have, and on the right it was all the things that are feasible, and in the middle is the like things that are a user wants and are feasible.
Right.
And it's kind of the product manager's job to figure out all the things that users like, and the engineer's job to figure out all the things that are feasible, and then they
Yeah.
kind of work together to figure out the middle.
Right.
Because we certainly see a lot of feasible things that no user would necessarily like or want to see.
Right.
Let's go. Oh, here's a really good page explaining a lot of the symbols and stuff. Okay, cool. I'm going to bookmark that. Let's keep going.
Let's.
Okay. I'm sure we're going to end up using the Fermat test soon. So
Okay.
this is very similar to the fast exp procedure in section 1.2.4. It uses successive squaring so that the number of steps grows logarithmically with the exponent. Footnote 46. The reduction steps in the cases where the exponent e is greater than 1 are based on the fact that for any integers x, y, and m, we can find the remainder of x times y modulo m by computing separately the remainders of x modulo and y modulo m. multiplying these, and then taking the remainder of the result modulo m. For instance, in the case where e is even, we compute the remainder of b to the e over 2 modulo m, square this, and take the remainder modulo m. This technique is useful because it means that we can perform our computation without ever having to deal with numbers larger than m. Compare with exercises 1.25. The Fermat test is performed by choosing at random a number a between 1 and n to the minus 1, n between 1 and n minus 1 inclusive, and checking whether the remainder modulo n of the nth power of a is equal to a. The random number a is chosen using the procedure random, which we assume is included as a primitive in Scheme. Random returns a non-negative integer less than its integer input. Hence, to obtain a random number between 1 and n minus 1, we call random with an input of n minus 1 and add 1 to the result. Fermat test in, define try it a equals exponent a in a, try it, and then add 1 and with a random. So this is an inward. So this is kind of our first example of a method inside of the Fermat test function.
Right.
That's interesting. The following procedure runs the test a given number of times as specified by a parameter. Its value is true if the test succeeds every time, and false otherwise. So we have this fast prime function that takes a number and the number of times to run it, and then checks if it's true. Then it runs Fermat test, calls itself again after subtracting times from 1. Otherwise, it returns false. If you've ran out of times, it just returns false. Probabilistic methods. The Fermat test differs in character from most familiar algorithms, in which one computes an answer that is guaranteed to be correct. Here, the answer obtained is not only probably correct, is only probably correct. More precisely, if n ever fails the Fermat test, we can be certain that n is not prime. But the fact that n passes the test, while an extremely strong indication, is still not a guarantee that n is prime. What we would like to say is that for any number n, if we perform the test enough times and find that n always passes the test, then the probability of error in our primality test can be made as small as we like. Unfortunately, this assertion is not quite correct. There do exist numbers that fool the Fermat test, numbers n that are not prime, and yet have the property that a to the n is congruent to a modulo n for all integers of a less than n. Such numbers are extremely rare, so the Fermat test is quite reliable in practice. Footnote. Numbers that fool the Fermat test are called Carmichael numbers, and little is known about them other than that they are extremely rare. There are 255, interesting number, Carmichael numbers below 100 million. The smallest few are 561, 1105, 1729, 2465, 2821, and 6601. So all suspect to be prime, but not actually. Is that right?
Right.
Going on. In testing primality of very large numbers chosen at random, the chance of stumbling upon a value that fools the Fermat test is less than the chance that cosmic radiation will cause the computer to make an error in carrying out a correct algorithm, which is a real thing. Considering an algorithm to be inadequate for the first reason, but not for the second, illustrates the difference between mathematics and engineering. Good point. There are variations of the Fermat test that cannot be fooled. In these tests, as with the Fermat method, one tests the primality of an integer n by choosing a random integer of a minus n and checking some condition that depends upon n and a. See exercise 1.28 for an example of such a test. On the other hand, in contrast to the Fermat test, one can prove that for any n, the condition does not hold for most of the integers a less than n unless n is prime. Thus, if n passes the test for some random choice of a, the chances are better that even that n is prime. Our chances are better than even that n is prime. Or are better. uh, If n passes the, I'm just going to keep going. If n passes the test for two random choices of n, the chances are better that 3 out of 4, chances are better than 3 out of 4 that n is prime. By running the test with more and more randomly chosen values of a, we can make a probability of error as small as we like. What's the point of that paragraph?
Let's see. I think it's just trying to say there's just saying that variations of the Fermat test exist.
Yeah.
And there are ways of minimizing the error, and that despite not being completely accurate, it's pretty good for most purposes.
Yeah. Excellent. Keep going. The existence of tests for which one can prove that the chance of error becomes arbitrarily small has sparked interest in algorithms of this type, which have come to be known as probabilistic algorithms. There is a great deal of research activity in this area, and probabilistic algorithms have been fruitfully applied to many fields. With a footnote. One of the most striking applications of probabilistic prime testing has been the field of cryptography. Although it is now computationally infeasible to factor an arbitrary 200-digit number, the primality of such a number can be checked in a few seconds with a Fermat test. This fact forms the basis of a technique of constructing unbreakable codes suggested by Rivas, Shamir, and Edelman in 1977. The resulting RSA algorithm has become a widely used technique for enhancing the security of electronic communications. Because of this and related developments, the study of prime numbers, once considered the epitome of a topic in pure mathematics to be studied only for its own sake, now turns out to have an important practical application to cryptography, electronic funds transfers, and information retrieval. Do we still use RSA?
Um, some people probably do.
Yeah. I thought it was one of the weaker ones now.
Yeah,
Yeah.
it's but some people are lazy.
Yeah. Yeah. Okay. I'm one of them. So we got to exercise here. Most Lisp implementations include a primitive called runtime that returns an integer that specifies the amount of time the system has been running, measured, for example, in microseconds. The following timed prime test procedure, when called with an integer n, prints n and checks to see if n is prime. If n is prime, the procedure prints 3 asterisks followed by the amount of time used in performing the test. Cool. So I guess we can use it. Do timed prime test. What's a small prime?
17.
17. 1.
Oh, there you go.
So, let's see. What are table primes? Timed. A bigger prime. Okay. 103,079.
Sure.
So that took 27
Okay.
microseconds.
Gotcha.
That's that F that we're pressing. I haven't seen that before. I guess that's the argument report prime. Oh, okay, cool. Ah. Using this procedure, write a procedure search for primes that checks the primality of consecutive odd integers in a specified range. Use your procedure to find the three smallest primes larger than 1,000, larger than 10,000, larger than 100,000, larger than 1,000,000. Note the time needed to test each prime. Since the testing algorithm has order of growth theta of square root n, you should expect that the testing for primes around 10,000 should take about square root of 10 times as long as testing for primes around 1,000. Do your timing data bear this out? How well do the data for 100,000 and 1,000,000 support the square root of n prediction? Is your result compatible with the notion of programs on your machine run in time proportional to the number of steps required for the computation? Question. Okay. Okay, so we're going to have a for loop that checks for primes in 3 steps. We already have the Fermat test, the X mod. Timed prime test. This isn't called new line. I'm just wondering which function to use to test the prime.
Yeah.
I guess we can just do Fermat test and fast prime.
I would think so.
Couple it. So this uses X mod. We don't want to do it a number of times though. What's this prime function? That's what I need.
Might be something that we defined in a previous chapter or something.
We can use the smallest divisor, I guess.
Okay, I see. I think that's a function we previously defined too, but
Then we have the smallest divisor. Probably not a very algorithmic way to do this. So let's see if this works. Let's actually print something. Oh, unbound symbol runtime.
Okay, it might not be supported in that environment.
Going to. Well, let's see if I can just test if this is prime, if it returns. So it's going to do my return. Found square. Let's figure out it here. Yeah. Okay, so we can just write it in this box. Consecutive odd integers in a specified range. Okay. Use a procedure to find the three smallest primes larger than 1,000, larger than 10,000, larger than 100,000, larger than a million. Okay, so we just need the first three odd, or the first three primes, and we check every odd. And we can just call prime on it. So we probably need a number of times. Didn't we just have like an amount of times? N times runs the test a given number of times. So we can do. I just brought it back here for another definition. So some pseudocode is going to be we have two different loops, 1,000 to whatever, 10,000. And we also need some kind of internal state to track that we've gotten three primes at once when we're greater than 1,000 but less than 10,000, and then once that is true, then we go to the next. We start our loop again at 10,000 and go 0, 0, 1, 2. When we have those primes, we start again.
I think so.
So while loop because I forget. Oh, does Scheme have let blocks?
Does it have what?
Let blocks?
Yeah, we get into that. Section 1.3 gets into that.
Okay. Oh, we haven't done do yet, but that would probably be a good way. I guess we just need to do it super procedurally. There's 3 primes. I take start. Can you hear me?